In this video, we're going to have a look at Mac heap overflows. Mac uses different structures to keep track of the heap and what has been allocated in the heap. And the place to get some information is from a publication called Frac. Some of you might be familiar with this publication, others may not. But Frac is a very old publication. It's been around forever. And they have very technical articles that are published in Frac. And this information, a lot of it comes from Frac issue 63 in the 5th article. So if you look here at the top, there is a reference to that article and a link to that article. So if you're going to do a lot of reverse engineering and exploits on the Mac platform, I highly recommend that you go and read this article. Now, remember that if you had an old Mac, then you would have slightly different structures, etc., because the older Macs had the PowerPC chips from IBM. The newer ones, 2005 and newer, all have Intel chips. So if we look at the simple program here, you'll see what I'm doing is I include some standard libraries, and then I include a pointer to something called the malloc zones. So the malloc zones are the different regions that are used by malloc. So it's declared as an extern unsigned. In other words, this is a pointer that's external to my little program. I then have my main function, pretty standard stuff, and I define 3 pointers. First, I define 2 pointers for buffers. One of them is going to be small, and the other one's going to be large. So here's my first pointer, P1. Define another pointer, P2. And then I also define a pointer, P3, which I'm going to use to overwrite some function pointers in this malloc zones. So how does this program work in practice? I start here. I allocate 64 bytes. We said we're going to allocate just a little. A little bit in this case is less than 500 bytes. So you can go 2 bytes and you can go up to 480, 490 bytes or so. And that is considered a little bit. And then I have this loop. I say while P2 is less than malloc zones. So in other words, I'm going to keep allocating until we're past the address of malloc zones. I'm trying to overwrite something here, and I'm using a large amount of memory. It has to be more than 16 kilobytes. So I say, all right, allocate roughly 24K. And keep doing that until my memory address gets to be greater than the address of this structure. Now that I'm above it, I want to overwrite P1 until we have overwritten some function pointers that are stored there. So what do? The first thing I do is I set P3 equal to P1. So I have this third pointer, and I'm going to set it equal to this guy. So now, while it's less than that address, plus 48, in other words, plus a little bit because I want to overwrite something right at the start of it. Just keep on allocating your memory. And here's how we do that. We are going to write 4 A characters, and the hex code ASCII is 41 for an A. So write 4 A's plus P3 minus the address of malloc zones mod 26 times 01010101. So here's what this is going to do for you. This is just something that I did to make a pattern in your memory. So what I'm doing here is I'm just writing out a little bit at a time, and it will write out 4 A's, 4 B's, 4 C's, etc. until it gets to Z, and then it will start back at A. And that should allow you to more easily figure out exactly where you got into malloc zones and into those function pointers. Now, there are a lot of people that would just print out all A's. The only issue with doing that, it's a little bit harder to figure out what was that address anyway. So here I'm just writing sets of 4 because 4 bytes is 32 bits. So that will give you a 32-bit address. So when the program crashes because you overflowed something, it will come up with an error message and it will say, all right, here is the address that I couldn't access. And it's going to come up with something like all C's or all A's, etc. And you can use that as a starting point to figure out that offset in order to crash the program reliably and in the exact way that you want to. We've talked about differences with the Macintosh. Things are slightly different with the stack vulnerabilities because of a non-executable stack. And things are slightly different here because there is a different set of structures that keep track of the heap. Other things are pretty much the same. If you look at format strings, errors in the kernel themselves, it's all the same sort of thing on this platform.